Okay, in this video I'm going to show you how to do another question on moments. This one is a bit more difficult, but I'm going to show you how to do it. So, a non-uniform rod AB of length 20 centimeters rests horizontally on two supports at C and D, where AC equals BD equals 4 centimeters. The greatest mass that can be hung from A without disturbing equilibrium is 8 grams, and the greatest mass that can be hung from B is 10 grams. Find the mass of the rod and the distance of its centre of mass from A. Okay, it's really important to read this carefully because you might get confused by this G, thinking that that's G as in acceleration due to gravity, but because they're talking about mass, it definitely means grams here. Now, first thing to do is draw a diagram. Now, really, we've got two different situations here. We've got the situation in which we're hanging something from A and the situation in which we're hanging something from B. This isn't, I think perhaps this isn't completely clear that these need to be considered separately, but that is what we need. Otherwise, there's not really any way to work it out, so that must be what it means. So let's talk about the first situation first, where we're hanging something from A. So we've got our rod here, AB, and we've got two supports at C. Let's call that one C and let's call that one D, and we know that that distance is 4 centimeters and that distance is 4 centimeters, which means if the total distance is 20, this in the middle must be 12 centimeters. Okay. Now, we can assume it's in equilibrium now, but the greatest mass that can be hung from A, so if we're hanging something from A, we're going to say that's going to give a force downwards at A, and that is a mass of 8 grams, so we can write that as 0.008 G newtons. Okay, so to write something in newtons, we have to convert masses to kilograms and then times by G. So this time G, I do mean that acceleration due to gravity, which we're going to approximate at 9.8. Okay, and if this is the greatest mass that can be hung without disturbing equilibrium, that means that it's about to tip, and it makes sense to say it's about to tip about C. So there's definitely going to be a reaction force at C. But if it's about to tip about C, if it's really on the point of tipping, that means the reaction force at D will be 0. So it's now only not really resting on D at all. It's actually just about to come off from D. But we do still have the weight of the rod itself, but we don't know what that is. That's what we're trying to find out, the mass of the rod and the distance of its centre of mass. So it's non-uniform, so we can't assume, as we often do, that the mass acts at the centre. So let's just put it here. It's probably somewhere between C and D. That would make sense. Let's call that mg, because it's the weight. We're looking for the mass, which will be m, but here we're marking on the weight, so it's going to be mg newtons. And we look for the distance from A, so let's label that on our diagram here as x, and we're looking for m and we're looking for x. Okay, so we're going to need, if we've got two unknowns, we're probably going to have some simultaneous equations to solve here. But we can start by setting up one of those equations by looking at this initial situation. Now, let's take moments about C, because that's where it's about to tip. That makes some sense. So let's say we're taking clockwise as positive. So we've got this weight, which will be clockwise if we've guessed correctly about where it's going to be. Doesn't matter if we haven't guessed correctly. If this x will still, if we use everything properly, this x will give us a distance from A, which is what we want. So it doesn't matter if where we've drawn it isn't right. It'll all come out. Okay, so taking our moments about C, we've got our positive mg, and now we need to be careful here. X is the distance of the weight force from A, but we are taking moments about C. So this distance here is going to be x minus 4 centimeters. Now, normally we would change these into meters to keep everything in our standard units, but we're going to end up with some very difficult to deal with decimals if we do that, so I'm going to recommend that in this case we keep everything as centimeters. Now, because we never really give a unit, it doesn't matter. It's okay, since everything is in centimeters, to keep all of our units in centimeters. So we're going to say that this distance is x minus 4. That's the distance of the weight force from C. Now, that's the only clockwise moment that we have. So now thinking about anti-clockwise, it's going to be equal because it's in equilibrium. We are going to have this force of 0.008 G, and that's just going to be times by 4. So again, everything in centimeters, it's fine to keep that as 4. Now, you'll see that quite conveniently the G's will cancel here because we're only really thinking about forces that are related to weights. So that's nice. So we end up with m x minus 4 equals 0.032. That's just the 0.008 times by 4. So that's an equation. We can now that we've got two unknowns, we need to find another one. So let's consider over here our other situation. So let's draw a new diagram. It's the same rod, AB, supports still at C and D. We've still got 4 centimeters here, 12 centimeters here, and 4 centimeters over here. We still have our weight in the same place. We're going to keep this as x to keep everything consistent. And now, but this time, we're thinking about how much can be hung from B. So we're hanging a mass from B of 10 grams. That's going to be 0.01 G newtons. And this time, if we're hanging something from B, we can imagine that actually it would start to tip about D. So the reaction force now is exclusively at D, and this time the reaction at C will be 0 because it's about to tip about D. It's not really resting on C at all anymore. So on this one, we're going to take moments about D. That's the point at which it's tipping. So again, clockwise we can keep as positive. And we've got this clockwise one here, 0.01 G, and that's 4 centimeters away from D. That's the only clockwise one we've got. Then anti-clockwise, we've got, again, it's in equilibrium, so we want them to be equal. We're going to have mg. Now we need to be careful thinking about what this distance is, because we want it in terms of x. So we think about this distance is going to be all of this, so 16 centimeters minus x. It's going to be 16 minus x. And that will leave us with the distance from D there. Okay, so simplifying this again, very nicely, G cancels out for us, and we end up with 0.04 equals m 16 minus x. Now we've got two equations. We want to solve these simultaneously. I think the easiest way to do that is to make one of them in terms of, or with the subject of m. So let's say m is equal to over here 0.032 over x minus 4. And now I can substitute that in over here. And I will end up with 0.04 equals, now I'm taking this m and the rest of that there, 16 minus x. Okay, so now I just want to solve this for x, so I'm going to do 0.04 divided by 0.032, which is going to give me 5 over 4. I'm also going to multiply through by this x minus 4, and I'm going to be left with 16 minus x on that side. Expanding out this bracket, I get 5 over 4x minus 5 equals 16 minus x. Adding x to both sides, I get 9 over 4 x minus 5 equals 16. Then adding 5 to both sides, I get 9 over 4 x equals 21. Then 21 times 4 divided by 9 gives me x equals 28 over 3, which is 9 1/3. And that was the distance, and we kept everything in centimetres, so it's 9 1/3 centimetres. We also needed to find the mass, so let's substitute that back in. Might as well substitute back into this one because it's already equals, so we're going to have 0.032 over 9 1/3 minus 4. So if I just minus 4, 0.032 divided by that, and I end up with a mass of 0.006, okay, which is 6 grams, because that was kilograms. Okay, so the mass of the rod is 6 grams, and it is 9 1/3 of centimetres away from